Right. Go ahead, Vladimir.
Okay. So I'll be presenting the DeepSeek-R1 incentivizing reasoning capability in LLMs via reinforcement learning paper. So this is the paper that kind of made a lot of noise and maybe even made NVIDIA stock crash in the past month. So I figured I would like to see what's going on here.
You're
But
not going
really,
to talk
it's
about the
actually
stock crashing, are you?
actually I should have put a chart of that.
It's an interesting
Uh,
phenomenon as well. Sorry.
yeah. But yeah, so this paper is actually like a string of many other papers they've done over the past like year. And this is just kind of, I guess, the real reason why the stock crashed and like it made so much noise, in the news is because they basically were able to get the reasoning component of it to work on par with OpenAI reasoning LLMs. And this was kind of their open sourcing and showing how they were able to kind of do it. So basically, yeah, that's kind of what we're going to be going through here is, uh, what's an LLM and how do you make it an LLM reason using RL, and then how they got to this step by bootstrapping from their previous models, basically starting with DeepSeek V3 base model, which is just an LLM with no reasoning. And then they kind of went through a few iterations of different reasoning models, which is the R10, and then the R1, which is kind of their state of the art model that made all the noise. And then we got obviously some benchmarks that they compare their model against OpenAI models, and then a bit about distillation to smaller models. So I guess I'll start. So, like, for those not familiar with large language models, essentially a large language model is an autoregressive function that takes some prompt or input sequence of tokens. It's called QI, and it outputs another series of tokens. Okay, your answer to whatever question you have, as let's call it OI. And there's no thinking involved there in the sense of the model doesn't have any thinking inherently to it. It's just a mapping from your prompt to some output. So the idea with the reasoning models is let's have the model actually have some chain of thought or thinking before it actually outputs our final answer that we're actually going to use as an answer. So it's still the same model, as it's still an LLM fundamentally, but now we're using this LLM as an actor, and we're training it to kind of generate a chain of thought policy that will lead to a better answer. And so basically, we just introduced this concept of chain of thought uh, to the output of the model before we have an answer that we can use. So, and I think for OpenAI, until the release of DeepSeek, they actually didn't show their chain of thought. So that was all hidden. And you just saw this answer that took multiple seconds to generate. So the reason it took multiple seconds to generate the answer is because there's actually more stuff being generated, which is the chain of thought that they didn't show. I think now they have some models that show it. So any questions on this?
So, is there like architecture for the chain of thought? Are you going to discuss that?
So there's actually
That
no
looks
architecture.
generic
It's
now,
this.
right? Mhm.
Yeah, it's the same. It's the same model as the DeepSeek V3 base. So the architecture is the same.
So, but
They just
once you
use
get the
RL.
output of this DeepSeek V3 base, there's something else happening with your. It's not just going to output. Um, yeah. So, what is hidden behind this chain of thought algorithm? I guess that's the question.
Yes. So essentially, they add reinforcement learning to this. So they have two rewards, and this will get kind of address your question
Hmm.
to some extent. So basically, they have two different types of rewards. One is the accuracy reward, which is basically the how accurate it responded with its final answer. So that gets computed on OI. And what they use for that is just rule-based verification of correctness. So like math problems, leak code problems, things that could be just computed automatically if it's correct or not.
Hmm.
And that gives the reward. But then the other part, and this is where chain of thought comes in, is they have a format reward where they force the model to put chain of thought in between, tags think, and then your final answer after that is enclosed in answer tags. So basically, this format is forced on the model output using just reinforcement learning.
But then you have
And
to train it with this type of output, right? So you cannot just feed in the sequence of tokens now. You have to, um, yeah. How do you train?
uh,
How do you produce data set that does that? That's kind of probably the question I have.
well, so this is kind of the big thing is that before you would have carefully crafted like human crafted data sets where you have some sort of template for your chain of thought, but here they don't have any template for this chain of thought part. It
Hmm.
just figures it out on its own based on how good your answer is. So they actually use pretty standard like RL with some modifications. I don't know if that answers your question
No,
or
but
not.
like if the model can have anything it wants in this think from think to think, right? Then it's gonna just have most likely garbage there, unless you actually put a loss function or you train it somehow to have produced this thinking part.
Right, but you don't know what the thinking should be. So the thinking is you prevent the thinking from being just kind of noise and jarble by using the rewards from your answer to kind of guide it towards
I
you
guess
know
let me just maybe rephrase it.
correct
Let's say
thinking.
you take a large language model, out to the transformer, right? And then you say, okay, I'm just gonna call the state in some hidden layers as thinking part. Yeah. Well, what's wrong with that? Well, because that thing, that this encoded information there has no language representation to it. It has some internal encoding of the correlations between whatever tokens you're considering. So there's no thinking. You cannot put a loss function to that part. So I mean, I understand that if you feed it with the data, which has both answer and the thinking process, then you can train on it. But I'm just having a hard time figuring out how you can uh, uh, not have a loss function on the thinking part and still expect it that it will generate some coherent thoughts.
Yeah, this
Yeah,
is
I think
what is
that
called
that's
zero-shot learning, as far as I remember, right, Vladimir? Like zero shot. So you didn't train for that, but your prompt that is represented at the bottom kind of guides the model to get some output, right?
No, but thinking part appears after the prompt, so it is at the output side. Um,
yeah. So thinking
Answer is both on
and
the
and
output
answer
side.
is actually all just one output sequence. So again, this is autoregressive model. So you give
Hmm.
it the prompt and then you just kind of feed what it's outputting back into it to generate next token.
Hmm.
So this chain of tokens that it generates, it's both the chain of thought plus answer. And then through the reward format they have imposed on this thing, you have basically some part of this designated as chain of thought, and then at the end you have some part that's designated as this answer.
Hmm.
So I think in terms of like providing direct rewards to the thinking part, I'm not sure to what extent they do that. I was reading another paper, the paper where they introduced the group relative policy optimization, which is the RL method that they use for this. They do have a way of going from, they basically train a model to go from like the overall reward for a given answer to, per token rewards in the answer. And then there's another step where they somehow do it to get like a reward for the actual thinking component. But that wasn't, they didn't really describe that in too detail. It was like one paragraph with no equations.
Sure.
But besides that, I don't think they have any other like loss function per token for the chain of thought. It's more of like an exploration discovery process, so as to get to the answer having a higher reward. So I mean, I think you can think of it as when you're trying to like just you're doing your more standard RL problem. Let's say you need to like find on a 2D grid, some tile that has a high reward, and then your other tiles don't have any rewards. So your agent is trying to kind of find like a path that that leads to the discovery of this reward. So I mean, the path itself doesn't have like rewards everywhere, but the path is important to finding that reward. So I think this is kind of the same concept where you have a path of chain of thought that leads to discovering a reward, which is the answer. But there isn't like a template for the path that it discovers. It just discovers the right path.
Vladimir.
Oh, I think I understand it. So it's kind of doesn't care to give a high, a low loss function for the next token or next 100 tokens, as long as there is a good loss for the small loss for like eventually at some time, at some later token, which you would call the answer. So it's kind of, it doesn't matter what it has in between as long as the final answer is correct. And then you give a high, you, you give a good grade to that and the low loss, and then it has to go all the way back, propagate it backwards, and then readjust all the weight. So it seems like a very difficult computational task to back propagate this from the final answer, right?
Yeah.
I mean,
I
that's
think
the
this will
problem in the
get more clear
reinforcement
with like,
learning. Right? Dan was saying something. I cut him off, so he should just say it.
Oh, no. My question dovetails with yours very well. It sounded like you said that the chain of, I'm sorry, that the contents of the chain of thought are more and more tokens that are used in getting to the answer. So essentially, the full answer or the full response is lots of tokens for the thinking and then some tokens for the final answer. I guess the question that I have is, gosh, is the thinking, those tokens that it generated, are those essentially put back through the model again? Essentially, is it augmenting my prompt with its thinking?
Yeah, that's how I understood it.
I think the thinking is could be more viewed as like a prior from which you generate the answer. So it finds the right kind of trajectory to go through in terms of token generation autoregressively up until it generates the answer, and so it needs like a proper prior starting point to generate a better answer.
No, but I think Dan's question was like, are you reusing the same network to get thinking and then answer, or and then you keep reusing it to generate more and more tokens, or is it some kind of bigger network that is only outputs thinking and answer and then only inputs the prompt? Do you feed back
Oh,
the
I see. Yeah. No, it's
I don't
all
know,
just
but I would
one
imagine you should do
LLM
something like
that
that.
does this. Yeah, it's just one LLM. You feed into it the prompt, and then it starts outputting, its output tokens.
Yeah, but how many
But the
of
thing
those
is, then you start refeeding, so let's say, you have your prompt, you feed it in, and then it generates some tokens, and then the last token gets refed into the LLM to generate the next token. And so it kind of auto regressively generates, next token, next token, next token. And then that generates like your whole chain of thought plus answer. So that was kind of like why I had this diagram here, where the DeepSeek v3 base model doesn't really do a lot of that, feeding back the tokens. It's just kind of, you feed the prompt in and you get your output tokens. Whereas with chain of thought, it's kind of taken in what it has produced already, like at each step, and then generates more. And so basically you can run this model for like infinity time, just, keep inputting whatever it just output and generating the next, chain of thought, as it's called, or the next token.
Yeah, but at some point you should say that's enough of thought. Give me the answer. So and
right, yeah. So that's why I think they have the rewards, the format rewards,
right.
Is that you need to have these tags in your output somewhere.
Yeah. So it looks like
And then,
architecture is completely the same. It's only the data set and what the loss function is different now.
yeah, the architecture is identical. So they
Right.
literally just copy the architecture of the v3 base LLM, but now they do this RL based fine-tuning. So if you're familiar with like the previous iterations of trying to make these large language models like more human friendly, OpenAI did reinforcement learning with human alignment or human feedback, RLHF. That was sort of a similar thing as they're doing here, except there they actually provided, like humans provided a template. And I think this is what you're getting at, Vitaly, is that
exactly.
they had a template for chain of thought, they had a template for the answer, and that made the model kind of know what to optimize at, like all the way through at each step. Here they kind of dropped that, human, like basically hand feeding to the model, and they have it just discover it on its own. And I mean, in future slides, you'll see that there's downsides to this as well. So just these rewards, being optimized through RL is not going to get you like human friendly reasoning. So yeah. So okay. So back to the rewards. So there's the rewards that you can easily verify using LeetCode or math solvers, and then you have these format rewards. And then they use these rewards through the group policy, relative policy optimization method, which is basically just the PPO RL method without the value model. Then the reason they dropped the value model is basically to make this more efficient, because essentially the value model has to be the same size model, as they claim, as the policy model, and the policy model is the v3 base model that they're optimizing. So yeah, so you have the policy model which is again the v3 base model that you take that's already trained on a lot of text, and then you use that model as your actor in the PPO method, where you have some query, you generate outputs, and these outputs normally would be evaluated by the value model, and then they would also go through a reward model, which is trained beforehand, basically to compute some meaningful reward on the output. But during the RL method, this is a fixed model. And then you have your reference model, which actually just computes the KL divergence between your initial policy model, like basically, let's say the v3 base model as like the starting state of that model, and whatever your update to the policy model is. And the reason you want to have this KL divergence between these two is that you don't want your policy model to significantly deviate from the already highly trained v3 base model, because like with RL, like the model could just go on some trajectory, and its performance overall will degrade. So you want the RL to kind of improve for reasoning, but you don't want to lose what's already learned by the V3 base model, so that you don't have forgetting. So in the PPO method, this all gets combined through GAE, which I'm not going to get into, but ultimately you get this advantage value, which goes back to your policy model, and that trains it. In the GRPO case, they drop the value model, and they just use the reward model to get rewards, which then get, again, computed to advantage values, and that goes to the policy model. And then the KL divergence is the same, but it goes directly to the policy model to penalize significant deviations from the original reference model. So more in depth on this part. So the GRPO model basically optimizes this equation, which comes from the PPO. And this is kind of their pseudocode for this algorithm. So again, I already described what the policy model is. So how do we compute this advantage using the reward model? So the advantage is computed by basically you take some input prompt Q, and then you basically sample the policy model for different outputs for the same input. And you're able to sample the policy model is because the outputs of the LLM, before being tokenized, it's just a softmax. So you can sample that softmax distribution with, let's say, different temperatures that control for randomness. And so you can basically sample as many as you want outputs from that distribution that is generated by the policy model given some input. So once we have multiple outputs, now we can use the reward model to kind of compute a reward for each output. And then, each reward is basically standardized by the mean of all of these rewards and the standard deviation of these rewards. Again, keeping in mind that this is all for a single input, same single input. And that gives us our advantage values, which go to the policy model to optimize it through this equation. So AI is your advantage value, and then it's weighted by the likelihood of the current policy that we're updating, which is pi theta over the pi theta old. So kind of to understand what this is doing is basically if the advantage is positive, and then your distribution is more likely than your older kind of model to increase, then this increases, and vice versa for negative advantage. They also have
pi is your transformer, right? So this pi is your transformer, right? It takes some input Q and then produces output O. Is that what we have here?
Yeah. So pi theta is actually like a distribution because it's a softmax output.
Yeah, that's
so
what you get from
they're treating it as
transformer.
that. Yep.
But a distribution over OI, over outputs.
Yeah, I think overall the all the tokens.
Okay, and so and then here you have two different transformers where parameterized by this theta, right? New and
Yeah.
old.
So yeah, the old. So you're taking multiple gradient updates to pi theta. So that happens like here. So initially they're the same, but then after the first gradient update, pi theta changes, and then pi theta old is kind of like the previous version.
But again, I think I'm still confused. So policy model is the transformer, right? So you input some Q and output some possible outcomes, and you said it's weighted by softmax so that they all add up to 1. That's fine. But then somehow you want to use this information to adjust your policy, and that's what the arrows back look mean, right? And so
Yeah.
what is it exactly? How do you decide? I mean, you need some kind of loss function to decide of how to update the policy model, and that's would be your reward model, or
Yeah, so this is the loss function. Because you have your advantages, which is basically the rewards, and now you want to just propagate them through the policy. So
okay,
yeah,
but
this
then
is
those rewards are calculated based on what you get as an answer. I mean, I think you already kind of said that, right? So you get the answer. If answer
yeah.
is inconsistent with the answer that you want to get, then you give it, you adjust your model, but you don't want to adjust it too much. You don't want to just retrain it from scratch. You just want to say whether the answer was good or not, something like that.
Yeah,
Well,
I guess, yeah. I guess your question is like, what is the purpose of like this the pi theta over pi theta old? I think that's to basically weight the advantage value so that it doesn't change too much and it changes in the right direction. And that's why they have the clip here to make sure that if the newer policy changes too much in one direction or not, it gets clipped by uh, some smaller values.
yeah,
It's
so
a
that
ratio. Okay, go ahead. Sorry.
so that clipping is to prevent major changes, right? But I think what you're looking for is everything in DKL, right? So that's the loss. Like you produce a bunch of different answers, the same prompt. Initially, in the first step of the learning, they're all going to be junk. So you go away from that gradient because the reward sucks, and then as you progress, you go away from the bad gradient. You start finding a good gradient, hopefully, right? You start producing good answers. You take the best of those, and you go towards those better gradients, right? And so you continually reward and go away from old to just theta. Old is the previous run, and theta is the new one. At least that's how I'm understanding it. I'm a little confused what pi ref is. Maybe you could speak more about that. But that's how
But
I'm
then what? That
understanding
makes
it, right?
sense, Jacob. But why do you need this? Why do you need to worry about old at all? All you worried about the performance of the new, right? I mean,
Because you want to see how you're improving, like from the last run
is old the last run, or but that's not what Vladimir said. He said old is the regional state. I mean, you just want to,
right.
you want
Yeah,
to do
there's
gradient.
always, if you learn till infinity, there's always, the original is just, every moment in time is the initial condition for the rest of the learning, right? So old is
Okay, so you think the old is the previous time step then? It's just whatever wasn't
that's how
previous.
I understand it. But I mean,
Okay,
correct me if I'm wrong. Sure. So,
but then no, but then because here they want to take a gradient of this because this is the loss, and so when you take the gradient of this will be trying to minimize this guy with respect to thetas, and
well, the
so
loss is DKL, right? Which old is not in the loss, but
which one is?
that, can you
Oh
talk
no,
about what?
no, I think it's not just DKL because everywhere you see theta is your loss because you can kind of differentiate equation one with respect to theta. And theta appears in both DKL and in the summation. But you're right, maybe the
Okay.
reference will tell us, what is pi reference?
Yeah, I think the confusion is like pi theta and pi theta old. This is actually like your softmax over all the outputs, whereas AI is just a single directional value. So like this operation basically just spreads AI over all the different outputs across the distribution, softmax distribution.
But there are two distributions.
Um,
There's a softmax distribution, which is pi sub theta as a function of OI. It's normalized. If you add over all i's, you get 1. And there is pi theta old, which is also a normalized distribution. So both of them are normalized distributions, and somehow you kind of divide one by another, which I don't understand. Why would you want to divide Um, yeah, and then
Yeah, but in terms of
Mhm. Go ahead. Sorry.
yeah, in terms of like the DKL, this is and like PyRef, this is purely a regularization term to prevent the policy from like steering away too far from the reference model. So this is
Which
not the main loss. The main loss is this ratio of pi theta old times the advantage value.
no, it's
So
still some
I guess I'm
constraint.
confused there because so I thought pi theta over pi old was calculating like a percent change basically. So major changes in the model aren't necessarily good. So you clip them. And then the loss is DKL. How much does your answer diverge from a good one, right? Because so in the beginning, you can put anything you want between thought formatting, right? And you don't want to necessarily reward those horrible thoughts, right? So like those need to be initially all your A's are going to be bad, and then you keep learning and you go away from those bad gradients from DKL, and you don't want to change the model in huge leaps, so you're clipping large percent changes. At least that's how I understand it. I
Hold on.
definitely could.
The model doesn't output AIs. The model output OIs. OIs are horrible.
Sure, but they horrible OIs lead to horrible AIs, right?
Okay, so you're saying the OIs are actually your chain of thoughts and AIs are their final answer. Is that how you thinking about?
No,
So like,
AI. Yeah.
yeah, basically like the advantage value gets applied to each token in the softmax distribution as like it depending on how much it improves, how much more likely it is compared to the old model. So if it's discovering certain tokens to be more likely, then those get more of this reward. But
Is
yeah, I
AI
think
a function of OI?
AI is well, yeah, ultimately it is a function
Okay,
of OI.
so you are trying to optimize some function of OI because AI is a function of OI, and actually it's a function of RI, which is a function of OI. And then you weight those A's by the ratio of probabilities, which is confusing. I don't know why would you want to weight it by the ratio of probabilities, because P theta OI is a probability of getting token OI. So your answer is actually sitting in OI. In the output.
Yeah.
Okay, that makes sense.
Yeah, I
But
guess
then,
I'm not 100% sure why they're doing this. This is more of a PPO method. Like this is not something that they introduced. But
right.
yeah, I would need to look more into that.
Okay, good.
But yeah, generally the pseudocode is you have your peer reference. So this is kind of going back to the question of what's the point of peer reference. Peer reference is like more of the more older initial model. So you start with pi theta initial, and in the very outer loop, you have pi ref being that basically model. And then you go into the loop where you start sampling outputs from inputs, computing your advantage values, and then in the inner loop doing the gradient updates to your policy network. So PyRef is really like a really slow changing model that's mostly fixed. And again, the purpose of PyRef is just to make sure that this RL training process, it is controlled. It doesn't deviate too much from the
Oh,
original.
I see. I see. So the PREF is what you're starting with, right? It's like initial state of the model, and then you're trying to train
Yeah,
it
yeah.
to be better in providing, in whatever AIs represent, having some more advantage point, yet not so far away from where you started, and that kind of controlled by the Lagrange multiplier beta that tells you, well, you don't want DKL to be too large. Okay, now that makes That makes sense.
Right, because you don't want the large language model that you already trained, right, on a lot of tokens, like the whole internet. You don't want it to forget what it learned while you're doing this RL, which RL is being done on a much smaller scale in terms of amount of data compared to the training you already did. So you want to make sure that you don't forget what it has already learned, but you kind of enhance it with reasoning using RL. So that's kind of the idea there.
Okay, and then the ratio probabilities probably also makes sense because you can think of probability in the canonical ensemble sense. It's like e to some e to the minus beta h. I don't know, some exponent, and then the ratio of those exponents is nothing but e to the difference in the exponent. And so this is kind of similar to what things like softmax do, but here at the level of probability. So I think this is the kind of weighting you want to give to AIs, not the weighting by the ratio of probabilities, or weighting to the exponent of the difference in what appears in the exponents there. Okay, makes sense.
Yeah, and also like this iterative group relative policy optimization, this is from their earlier paper, or maybe actually from like a different paper. So I'm not sure if they're actually even using the iterative part. Like PyRef could be fixed throughout this whole training process. So yeah, that's just kind of a note there.
It seems
Okay,
like you'd want
so
Py. Oh, sorry. It
Yep.
seems like you'd want PyRef to be sort of semi-fixed, like pretty old, but still moving, because as the model gets better, PyRef will also get better, right? I mean, you don't want it too recent, but you don't
No, I
necessarily
think
want
the
to keep
point
it.
is to keep it. I think that was the point. Like PyRef will be like what's V3 model, DeepSeek V3.
Okay.
yeah, that's the V3.
I think that because like if you let it go, it will just go, you know. You just want to train a model which is not very far away from V3, and yet it has the better, you know, thinking capabilities, which are defined by the first term in equation 1. So the second term tells me don't go far away. Okay, it still produce some, you know, V3-like outputs, but yet make sure that the answers are respected.
That makes sense. That makes sense.
Yeah, you don't want catastrophic forgetting, basically.
Sure. Because if you let the PyRef go, then it will just, the whole thing will just drift away, and then it might drift away. Okay, good.
Yeah, exactly. Okay, so after doing that training, they analyze, the improvement in accuracy, and there's like 2 different ways you can basically get outputs from this model once it has been trained. One is like the single response, which is denoted as pass at 1. So in that case, you give your question to the model and you let it think once, and you get your response out. You sample your softmax logits out once, and you treat that as your answer. But there's another way where if you have more inference time compute, then you can do what's known as like majority voting, where you essentially do multiple samplings from the softmax, and you see how consistent your answer is. So in that case, you basically take whatever the majority of the answers say as your correct answer, and that produces like a significant shift in your accuracy. As you can see here, it's consistently like performing better than just a single response. And they only do this on AIM 2024 data set. But yeah, so that's kind of like the main point I want to highlight here. Obviously, they also compare it to OpenAI, different models. So any questions on this? Okay,
Well, in
so
softmax at the end, there is this parameter beta that tells you, like, sets how confident you are in the final answer. So presumably, if you just collect a lot of responses, that's effectively means you are setting your beta to be, larger and larger, or temperature to be smaller and smaller. So maybe that's can be, this improvement can be reproduced by just adjusting this temperature parameter.
So I think in terms of the temperature, depending on how many like times you're sampling, I think there's like a different temperature that's optimal for the number of times you're sampling.
You can learn it.
In order to have like the highest performance.
Sure.
So that was like in another paper I saw that they're referencing. But yeah, you can sample with like different temperature. Okay, so that's one example of how you can leverage inference time compute to kind of boost your accuracy. Another is actually just due to the length of time that it thinks, so the length of your chain of thought. And this actually increases naturally with RL training. So this increase they found in accuracy as you go through training iterations, which is your x-axis, corresponds to a longer chain of thought reasoning. So this is average length per response. So the longer the model thinks, the kind of better the accuracy becomes. And this is a purely emergent behavior because, again, they don't enforce some specific length of chain of thought that it should have. So the model kind of steers towards policies that tend to think longer, and it finds on its own that produces higher accuracy.
So, but the thinking time is a parameter you can specify, yes?
I don't think so. I think they have like a very long maximum length of like tokens it can output, but other than that, there's no like explicit duration of
There got to be a parameter that sets how long you allow the model to think, no?
Yeah, I think
There is
there's like
special
an
token,
absolute
that specifies
Maybe a
the
special
amount of the
token.
answer.
Yes, maybe a special token that will
Yes,
just.
in the prompt we have
Yep.
it. As
What they
far
do?
as I
Okay.
remember.
Okay.
I mean, the model can output some special token if the model thinks that the answer is sufficient, as far as I understand it. Am I right, Vladimir?
No, but
wait, can you repeat the last part?
I mean, in the prompt, you have some prompt, and there are some special tokens that defines like the brackets within thinking and within in between some specially designed tokens. There is a thinking process of the model, and then the answer as well. If you get back to the slide with the prompt, I guess we can see it.
Yeah, but there's no token that specifies the length of like tokens it should generate.
I mean, the model can decide. You see, like answer here, and there is / answer, and I think the special token correspond to that keyword, and the assistant answer may be longer or shorter depending on like what model chooses, so to say.
Yeah, but you do not. It doesn't come with the input tokens. So I misunderstood you. So you do not say like in the input stage, you say, "I want you to think for that long. Give me the answer."
Yeah, I don't think there's anything like that. So the thing.
Well, then inside the model there has to be
tokens,
this time scale. So basically, my point is, if there has to be some time scale that's set in within the model learned. What's the most appropriate time or length of this thinking tokens?
Yeah. So again, I don't think there's any. At least I didn't find any evidence of them using an input like token or any sort of reward that controls the duration the chain of thought and response should be, or like the length of tokens that the chain of thought and response should be. But I think they do mention somewhere that there's like a really long token length cap on like how long it can be total. So I guess there's a hard limit there, but I think it was way larger than what they show here, which here the maximum is like 12,000 length. I think that I saw was like 32,000 or something. So I mean, besides a hard limit that's like really long, I don't think they have anything else really. And like realistically, there's no like there's no inherent reason why the model should, you know, think that it should like just generate tokens to the very like max that it can generate them. Because like there's no inherent reward to like have more chain of thought or less chain of thought.
Yeah, but I think they should. I mean, you can ask the same question depending how detailed you want to give the answer. You will produce two different answers. Like, what is quantum mechanics? I can
Yeah.
say it with
Okay.
very few
Yeah. I mean, I
tokens.
think current models they do somehow specify that.
So it
Maybe I'm
either
not
has to
sure
be
how OpenAI
specified.
does it.
If it either has to be specified someplace in something like input prompt, or the model was kind of learned already this parameter of how well it will answer a given question, how long it will think about it.
Yeah. I mean, okay. So I think there's definitely a way to like incorporate that. So the user can say think for 10 seconds or whatever that translates to number of tokens.
Mhm.
But I think in the case of R1, they don't have anything like that. So it's just think for as long as you need to improve the reward, and that's it. Okay, so those are kind of two examples of how they use inference time compute to increase their performance. One is just the model discovers to think longer, and the previous one was just majority voting. So let's sample many outputs as opposed to one. Then there's also the famous aha moment that everyone keeps talking about with DeepSeek-R1 0. And this is basically them saying that they discovered that the model discovers basically it has points in chain of thought where it stops like its chain of thought and says, I need to reevaluate my strategy because this is like a dead end or this is not going anywhere. So this is purely emergent behavior, according to the paper, that it generates this chain of thought, and somewhere in there they find these lines, such as the one you have highlighted here in red, where it says, talks to itself, wait, that's an aha moment I can flag here. Let's reevaluate the strategy for solving this question. So the question was a math question. If a is greater than 1, then the sum of the real solutions to this expression is equal to blank. And it starts one strategy, and then it at some point realizes that it needs to reevaluate and try a different strategy. And the cool part about this is that this is purely discovered through RL. So there's no like chain of thought template that tells it to try one strategy, try another, have like an aha moment. This kind of all came out as emergent behavior from just the rule-based reward RL that they're doing. And this also kind of goes back to the question that Vitaly had regarding what is the loss, for chain of thought, which again, there's no like direct loss because there's no template. It's essentially trying to discover successful templates for its chain of thought that will lead to better outputs. If that makes sense. And I guess the other point is they know that the model somehow starts using anthropomorphic tone, which is kind of weird. But yeah, I mean, when I first saw this, I thought like this has to be like I thought that the researchers put the red part in here, basically kind of like to say what the model is doing. But apparently the model figures out to say this on its own. So it's a bit freaky. Okay, anyway, so that's DeepSeek-R1 0. But in terms of being human friendly, it turns out that just this reward-based, rule-based rewards RL is not enough to get it to be human friendly, especially for the chain of thought part, because they found that it mixes languages. I guess it mixed Chinese and English. And besides just reasoning problems such as math and coding problems, it wasn't too good at like other questions that were more less logic oriented. So what they proposed was a pipeline to kind of go from your R10 reasoning agent to a more accessible to humans R1 reasoning agent, basically by bootstrapping off of R10. And the pipeline basically consists of, let's collect a small amount of tailored long form detailed chain of thought data from R10. So again, they're not like, they don't have a template, but they basically tell the model to answer certain questions, and then they handpick chain of thought outputs that to humans appears to be like the best. So chain of thought strategies that have like reflection, exploration of alternatives, good description of what it's doing. And then they further kind of annotate it and modify it to be language consistent and easy to understand. And this forms what they call the cold start data, which then they use to fine tune the original V3 base model. So this is not even the RL agent. This is like just the LLM that was trained on the internet. So they fine tuned that model on the cold start data, and then they kind of repeat the process again using this tuned V3 base model. They repeat the RL process to generate basically a new version of R10. And they repeat these steps like several times. So basically the pipeline is you have your initial V3 base model trained on the internet. You copy it to do reinforcement learning to get R10, first iteration. That's not very human interpretable. You sample from it, chain of thought, and make it human readable. And then you do fine tuning on, again, the original V3 base model, which then gets copied to like the next iteration of R10 training, repeat RL, do more of this sampling that is considered good for humans to understand. And I think they do this like 2 or 3 times. And like on the first trial, it's still the same the same reasoning logic problems. But I think on the second and the third iteration, they introduce less logic oriented samples, which they didn't really go into too details. So I'm not 100% sure how they did that or what the rewards were. But yeah, basically you have this feedback pipeline, and then after a few iterations, you get your R1 by just copying the weights, and you have R1.
So the cleanup part is done by human.
Yeah, so that's like the only part that's done by human. And
Okay,
again,
and
there's no like
human...
template. There's no template. It's just more of, again, so the key point to point out here is the RL part never gets human like human chain of thought templates or anything like that. They just fine tune the base model on these human altered chain of thoughts, human selected and human altered chain of thoughts. But that doesn't contribute to like the RL component of it. So the RL component stays the same. It's just that the V3 base model is now more like initialized on human readable outputs. Does that make sense?
Well, somewhat. I still struggling and understanding that. I mean, are you changing this base model and then use it as your reference model for training RL?
Yeah. So they literally just copy the weights from the V3 base and then apply RL.
Yeah,
And remember,
no, the
RL
first I
is
understand,
trained with,
but the second
yeah.
iteration, I
So
don't.
yeah, second iteration is a tuned V3 base model. So it's no longer the original V3 base. It's like a further tuned V3 base model.
And that's
That
exactly
is
how you tune it. So that's my question. How do you exactly tune it? So let's say I produce some DeepSeek-R1 zero responses, and then in the thinking part, there is a mixture of math and Chinese and English. I say it's no good, and then what?
Oh, actually, that's a good point. So I forget to include? I think I may have forgotten. So actually, for the second iteration, they I think add another reward penalty for not using the same language. Oh yeah, I think I have it here. So there's an additional language consistency reward that's added
So
to
how you
basically
want now
force
both
it to
things
use
to
the same
drift?
language.
You want R1 model to change, and then you want your V3 model to change gradually. So yes, because like in your loss
So,
function that you had.
so this is what
Uh,
I was trying to say about
yeah.
PyRef. I'm still confused. I feel like PyRef should
So maybe
drift.
it is drifting, but not.
In DeepRL that I've implemented in the past, like that is a hyperparameter to like control how often you're updating that reference. Cause like if it's super new, like there's no change and DKL is doesn't even exist, right? If it's close to 1, those ratios. And if it's too slow, you're constraining the model.
No. I think beta is fine by keeping this not to be like. Can you go back to this loss function that we are talking about, Jacob? Yeah, so you're saying if beta is 0, then you can just ignore this part. But if beta is non-zero, it just tells you, well, how far away from the reference model you can go.
I'm saying if pi ref is very close to pi theta,
Yeah,
DKL is, almost non-existent.
right. But they're not. The whole point here is to
Sure,
keep.
totally. That's what I'm
Yeah,
saying. But also if you don't update it fast enough, so you never update PyRef. So that's the extreme case of updating it too frequently. You update it every time step PyRef, right? You
yeah.
don't want to do that. What is what I'm saying. And if you never update it, you're also constraining your model because you only get so far away from the baseline and you don't learn past that.
Right. And the point is you do want to constrain it, but maybe you will allow it to move as long as it gives you something that
Yeah.
human
So like
approve.
I've seen in the past hyperparameters where like you update it every 100 time steps or every 1,000, whatever, depending on your case, right?
Sure.
So
Yeah.
Yeah,
So
I think that would be controlled by like the M parameter. So in the nested loop here, how many
Mhm.
times you want to update pi theta before you go to back to the outer loop and update your pi ref.
Oh, I
exactly.
see.
Yeah.
So there are two
Okay.
loops
Yeah.
there.
Yeah,
Okay.
there's actually 3 loops. Maybe I should went more in detail for this. So like you have your outer loop, which is fixing your pi ref, and then you have your second inner loop, which is generating the data that you're training on. And then you have your third inner loop, which is actually like multiple gradient steps to
Sure.
optimize pi theta. So
Okay. So we are running out of time. So, but hopefully we are.
yeah, so I'm almost done. So
Oh,
this is
okay.
just the benchmarks that they have comparing DeepSeek-R1 versus like OpenAI reasoning models and then also non-reasoning models. I don't know how much in depth you want me to go here, but like they have English, code, math problems, benchmarks. So it seems to be on par with like OpenAI 01, 1217 model, which I guess was the latest model at the time that they did this. Again, OpenAI has too many models at this point. So I don't know what the difference is between these. And then they also did distillation. So, and like real quick, so they distilled it to smaller models, again, using basically supervised fine tuning. as they do the same way, fine-tuning to the V3 base model. So this is on very clean data set that's human readable. And they found that they can distill the R1 model to much smaller models with better performance than the original model that they're fine-tuning.
Mm-hmm.
And I think here they just did the Quen and the Llama model. And then they did one ablation study where they basically said, can we use our RL approach on the smaller model to improve its performance versus, distilling the model from a larger R1 model directly. And they found that, the RL on the smaller model doesn't really work. So the performance kind of stays the same. But distilling from a much better R1, larger, better R1 model to a smaller model, that produces like huge improvements. And you can see that in like the last row here. And that's kind of the takeaway there. And I think that's all I have. Yep.
Perfect. Thank you, Vladimir.
Yep. Thank you.
Great. Any other questions, comments? I guess all the questions was. Thank you so much. That was very interesting. Let me